Thank you, Marka. Good morning, everyone. Happy Wednesday. So let's continue with nonlinear perturbation theory for large-scale structure. Let's start with a brief recap of what we discussed last time. So last time we talked a lot about the shape of the linear matter power spectrum and different quantities we can extract from it. So here I'm showing you the actual plot that corresponds to the lambda CDM cosmology, let's say best fit to the Planck 2018 data. So you can see these features that I described yesterday, that the power spectrum goes to zero linearly for very low wave numbers, and then it decays asymptotically as k to the minus 3 times log k squared, but for a limited range of scales, you will see that it has some sort of running slope. And if we look at the range of scales relevant for the BEO, then you can see that the slope is very close to the minus 3 halves, minus 1.5. Okay, this minus 3 halves, I thought that it's just interesting. It's a complete coincidence, but minus 3 halves also is a kind of scaling that appears in many other physical systems, like for instance, Kolmogorov turbulence in biophysics, etc. So I think it's kind of funny that the relevant power law here is also minus 3 halves. Okay, now another relevant quantity is the two-point correlation function, which is the Fourier transform of the power spectrum. So here I'm showing you the correlation function that I multiply by the square of the distance. So in that case, well, this representation is nice because then it enhances the BO feature. So the BO oscillations, they correspond to, well, as you can see, some sort of harmonic oscillations in the matter power spectrum. And if there were an exact cosine without any broadband, then their Fourier transform would just give you a delta function located at the frequency of the oscillations. Now, because you have the seal damping and also the broadband part, there will be kind of, instead of a delta function, will be finite peak. But yet you can see that this peak has, it's very pronounced in linear theory. And this is something that I'm sure you know very well, that is used in the BEO method of measuring the distances. All right. Other things that we discussed last time was the equation of motion for a generic dark matter fluid. So the idea was to be agnostic about the properties of the small scale structure. So imagine we don't know anything about dark matter. We only know that on large scales, its total energy density dilutes like 1 over a cubed. So we wrote down the most generic action, well, the most generic equation of motion that just follows basically from the continuity equation and the Navier-Stokes equation. Well, in this equation, where I was using the conformal time tau, you can see that it's very similar to Navier-Stokes equation. You have this extra dilution term that captures the cosmological expansion. Then one important feature here is that there is a stress tensor, and this stress tensor in principle captures the details of the small scale clustering. So the idea is that with this equation of motion, I would like to capture the presence of the halos and in general the effects of the clustering of small scales that are not present in linear cosmological perturbation theory. You know that in linear perturbation theory from Jean Lien's lectures that this would be, your description. Without this term, this would be your normal equation of motion for dark matter. Now this is the most generic nonlinear extension of it. And it turns out that, well, as I'm going to show you in this lecture today, that different terms in this equation of motion, this Navier-Stokes equation, they have also some scaling in terms of some small parameters. And turns out that the perfect fluid part of this equation is a leading order approximation. So it has the best possible scaling in terms of small parameters. And then the stress tensor represents a correction to it. So in some sense, this parallels the structure that we have seen in the electrostatic potential, where we would have a monopole at very large distances and then corrections in the form of the multiple expansion. So same way here, the perfect fluid part represents some kind of monopole, and then the stress tensor represents dipole and higher order corrections, okay? Well, in this case, the monopole part is going to be already very rich, and it contains a lot of interesting physics, unlike the usual monopole, which is kind of trivial. And our first task today is to really study the predictions of the perfect fluid part. Okay, so this is our first approximation that we're going to use to solve this equation. So we're going to drop the effective stress tensor, and we're going to solve the perfect fluid. And this method is called, well, the resulting theory is called the standard perturbation theory or nonlinear standard perturbation theory. And historically, this was the first attempt to solve structure formation at the nonlinear level. And basically, the idea was to start from the linearized equation for dark matter that Julien was discussing, and then to promote them to nonlinear level by accounting for the material derivatives. So this was the original motivation. Again, as we should all remember that this is only part of the answer, but historically people thought that maybe this would be all of the answer. Okay, so I'm going to use some convenient variables. So I'm going to switch to this variable eta, which is logarithm of the growth factor. And I'm going to use the letter theta to denote the properly normalized gradient of the velocity field. So, you know, in the literature, there is a distinction between small theta, like small theta that people use in linear perturbation theory is defined slightly differently. And, you know, in linear perturbation theory, people define this large theta that defines like this. But in my lectures, I'm going to define both thetas like that, so such that at least, you know, within this class, we're, you know, the notation is simplified. All right. Now, what I started discussing last time was that we can massage these two equations a little bit. We can take extra gradients to bring the Navier-Stokes equation into the form of the equation on theta, and then also use the Poisson equation for phi that has the standard form. So it doesn't have any nonlinearities in them. You know, it relates fully nonlinear quantities in a linear way. So we can use these things to arrive at a set of two equations that only contain the density contrast delta and the velocity divergence theta. And in that case, when we use the Fourier transform, because we have these material derivatives, you know, they are nonlinear, so we'll not be able to reduce this to something that depends only on one field. Now it will depend on a convolution in Fourier space of the two fields. So if we just follow, you know, straightforwardly the algebra, we're going to arrive at the equations that I wrote conveniently here. The first two equations, you will see that on the left-hand side, so the first equation is the Fourier transform of the continuity equation. The second equation is the Fourier transform of the Navier-Stokes equation, or, well, earlier equation in this particular case. And you can see that on the left-hand side, they have linear quantities. Right-hand side, they have this quadratic quantities, quadratic convolution integrals that follow from the nonlinear kernels dictated by the material derivatives. And now we can try to solve this system of equations. Well, the one thing that you will notice immediately is that it depends on these background quantities, the redshift-dependent omega matter that I introduced last time, and the logarithmic growth factor f. And there are two cases that will allow us to some simplifications happen. Okay. Okay, the first case is the matter-dominated universe, also known as the Einstein de Sitter universe. So this is the usual universe where the growth factor grows like t to the 2/3. Now t is the usual physical time, and this corresponds to omega matter being 1 and logarithmic growth factor being 1 as well. So in that case, obviously, these quantities will drop from the equations. The equations will become So they will not contain any time-dependent coefficients, so they will simplify significantly, and this is very nice. But obviously, this is a terrible approximation, right? Because we know that omega matter is 0.3, so this is not going to give us an accurate answer in our universe. So, however, there is another regime where you can get the same amount of simplification by assuming less things. So you can assume that omega matter is equal to f squared, and these things are not equal to 1, okay? In that case, also all the time-dependent quantities drop from these equations, so you only have time dependence in the variables you're solving for, not in the coefficients. And well, basically now you can solve these equations nicely, and it turns out that this approximation actually is satisfied quite well in our universe. So confusingly enough, in the large-scale structure literature, this is what people call Einstein de Sitter, and not the original one. So EDS in LSS. And even here, I must say that there will be an asterisk, that even this is not the end of the story. But this is the approximation that we are going to use from now on, that omega matter is equal to f squared, okay? So we're going to assume this in what follows. All right. To start off, let's set alpha to 0 and beta to 0, these integral kernels. Then we're going to arrive at an equation, the system of equations that will look like this. So from this equation, it's easy to see that they have a solution in the form theta k equal delta k equal to e to the eta times delta naught of k. Okay, so this is the usual linear adiabatic mode. And you can see maybe now the advantage of this representation, because now this solution is kind of obvious from these equations, okay? All right. So again, the nice part about this is that the equation doesn't have any time-dependent coefficients, which guarantees this factorization. Now, what are we going to do for the realistic case where alpha is not 0 and beta is not 0? So it turns out that since we don't have any time-dependent coefficients, this factorization of time dependence and k dependence persists to higher orders in the density fields. Okay, so in other words, we can solve this solution in a perturbative fashion. Well, basically looking for a solution in the form delta equal to delta 1. So this is our delta 1 linear solution. So delta 1 is delta naught times d plus. And then we can look for a correction to this solution once alpha and beta are not 0. That will take the following form. It will look like d plus squared times delta naught squared. And then the idea is to extend this to higher orders, and in general to look for a solution that will organize itself as a Taylor expansion in delta naught, right? Which seems to be reasonable, right? Because you have this right-hand side, which is small, and then it involves some nonlinear, well, quadratic combination of these functions. So if we take these ansatz and put this into the equations of motion, we will see that indeed it passes through them, and the time dependence at every order will be just, for quadratic fields will be d plus squared, for the nth order field will be d plus to the n. But however, as you can see, these different solutions at higher orders, like for instance, this would gonna call delta 2, this is delta n. So there will be not simple products of the initial field. There will be some convolution quantities, right? This is something that follows directly from the structure of this equation. So you have the convolution integrals here. So your solution also will take a look, will take a form of the convolution integrals of this type. So the truth is your solution will be slightly more complicated. It will involve some kernels. But the time dependent, the time dependence, the factorization of time dependence is something that will persist to higher orders. So in other words, we can try this ansatz. We can plug this into the equation of motion, and then we'll see that we will be satisfied for some values, well, for some kernels fn and gn, right? So at every order, there will be a solution provided that the integral kernels take a particular form. And we can find that if they take the following form, so fn as a function of n momenta, q1 to qn, and jn as a function of n momenta, q1 to qn, if they satisfy the following Recursion relations at every order, then this ansatz will solve the fluid equations. So at every order, at order delta to the n, you will see that this provides a solution at this particular order. So in some sense, this solution with these kernels that satisfy these recursion relations, it will represent a full, in some sense, exact perturbative solution in the form of a Taylor series to the fluid equations. Okay, and in particular, for the first non-trivial corrections, okay, we can write down delta is delta 1 plus delta 2 plus delta 3, and delta 2 will look like this. D plus squared times d3 q1, d3 q2, some factors of 2 pi, delta function, okay, minus q12. So I'm going to use notation q with the index 1 to n is q1 plus q2 plus etc. all the way to qn. All right, so q12 is q1 plus q2 times f2 of q1, q2, delta naught of q1, delta naught of q2, and this will be a solution to the fluid equation of the quadratic order if f2 kernel takes the following form: 5/7 plus q1 q2 over 2, 1 over q1 squared, 1 over q2 squared, plus 2/7 q1 q2 squared, q1 squared, q2 squared. Okay, a couple of comments here. So first of all, you will see this dependence on the momentum that goes like 1 over q, which seems kind of bothersome, right? Because we were discussing before how nice, for instance, in the fluid equation, you have the gradient expansion with a bunch of terms that go to 0 as k goes to 0. Now these terms blow up as q goes to 0. And this is the result of the, well, basically it's a consequence of the Poisson equation, right? Because delta, well, phi is delta over the Laplacian, so delta over k squared. So in some sense, this is a result of the Newtonian approximation, where gravity has an infinite range, and it, well, basically, yeah, there is no retardation effects, right, in the Newtonian physics, right? So this is the result of that, Newtonian gravity. Now, a second comment is that the dependence on q's that appear here, for instance, q1, q2, you can say it's q1, q2 times cosine of the angle between these two momenta. Now, so this doesn't depend on the angle between them. This depends on cosine. Let's say I'm going to call it theta q1 q2. This depends on cosine square of theta q1 q2. So you can see clearly that in the space of these angles, this is the monopole, this is dipole, and this is the quadrupole, right? So in some sense, these kernels that we obtained, they just realized the multiple expansion, okay? Now this will be the multiple expansion of the gravitational field. Okay. And now this is a good point to comment on this asterisk that I left here. What is the Einstein de Sitter approximation in large-scale structure? So the Einstein de Sitter approximation now will be to use exact D plus. So exact D plus that follows from omega mater from the Boltzmann equations and F from the Boltzmann, from the Boltzmann codes that don't satisfy this. So we used exact D plus in these expressions, but we use the kernels such as F2 and G2, etc. But Fn, Gn kernels that are obtained in the limit omega mater equals F squared. Okay. So this is already satisfied to, let's say, percent accuracy in the actual universe. Now, with this extra twist that we're using exact G plus, we can reduce the cosmology dependence of our perturbation theory to sub-percent level. So basically, the sub-percent level, this Einstein de Sitter approximation is very accurate. Okay. Yes. No, there is no intuitive reason. It just happens that omega mater in a lambda CM universe just follows from solving the equations that roughly F. So F goes like omega mater of Z to the power 0.55. And this 0.55 is something that comes from a combination of different factors that don't talk to each other, right? And you will have this big simplification in the equations of motion if this is 0.5, right? So this is just a coincidence, but it's a good coincidence. I mean, in principle, we can solve, we can totally abandon this and we can start solving this equation order by order. And what we're going to find is that different terms in these coefficients, they will have some time-dependent functions, right? So in principle, we can account for time dependence exactly, but it just makes the whole construction clumsy. But in principle, it's possible to do. It's not a big bottleneck. But as I said, this Einstein de Sitter approximation is already very, very good for realistic redshifts. This is already, per mile level precise. Okay, so you don't have to worry about this in most of the applications. All right, are there any other questions? Okay. Right. So now the algorithm is clear. If I want to solve, continue solving the fluid equation, we just evaluate these formulas recursively, and then we obtain the full exact solution in the perfect fluid approximation. And now we can compute the nonlinear power spectrum. So let's see how this computation plays out. Okay, paragraph 3.3, SPT power spectrum. All right, delta nonlinear is delta 1, delta 2, delta 3, etc. Now, for the first non-trivial correction to linear power spectrum, it's enough to consider only the quadratic correction and the cubic correction. Okay, so let's see how this is going to work out. Okay, so now we just have to compute the correlators of these different fields. The first relevant correlator obviously is just going to be the linear TU result. So the correlator of delta 1, delta 1. This is our usual P11. Then we'll find schematically a term that looks like this. It has delta 1 and delta 2. Now, remember that delta 2 is proportional to 2 delta 1s. So this correlator will have 3 delta 1s. And we know that for a Gaussian random field, this correlator will be 0. Now, if the cosmological initial conditions have some non-Gaussianity, which typically is generated in inflationary models, now this correlator will not be 0 and will produce some observational effects. And this is one of the channels how we're looking for non-Gaussianity in large structure data. So this is something that I'm going to discuss in detail in my last lecture. But for now, let's work in the context of the Gaussian random field. So this correlator is 0. We can ignore it. Then the first non-trivial correlator involving the nonlinear corrections will look like delta 2, delta 2. So we know that this is something proportional to 4 Gaussian random fields, so its correlator will not be 0. And then also we're going to find two terms that involve the correlator of the linear field and the cubic fields. And there will be two symmetric corrections. Okay, so these two corrections, they also have 4 linear fields involved, so their correlator is not 0. Now, it's relatively straightforward to compute the correlator of delta 2, delta 2 using the Wick theorem. So I'm going to do this schematically. So I'm going to say that this is f2 delta 1, delta 1, the integral of f2 delta 1, delta 1. Now, I'm going to apply the Wick's theorem. I'm going to find then 3 possible contractions of density fields in this expression. So for now, I'm just copying this. All right. So let's see. So the first possible contraction will be this. Second possible contraction will look like this. Now the third possible contraction involve density fields inside each integral. So this term will be trivial because if we compute the power spectrum, we know that from in Fourier space, this correlator will involve a delta function of the sum of the momenta here, right? And the sum of the momenta, so that means that Q1 plus Q2 here in this expression will be 0. And from the expression in its kernels, we know that the sum of the momenta should add up to k, right? So it will be something that only contributes to k equals 0. But k equals 0 by definition corresponds to the background, right? And the background we already fixed. So that's why this contribution will be trivial, right? You can think about this as a bubble diagram in field theory to normalize the background. Okay, so we don't talk about this term, but these two other terms will give a non-trivial contraction. And if we just work out the algebra and we use our expression for the linear matter power spectrum, we are going to find that delta 2 correlator will give us an integral, convolution integral that will look like this: k minus q squared p11 of q p11 of k minus q d3q or 2 pi cubed. And you have this factor of 2 because of the symmetry, right? Because of these two possibilities in the contractions. Okay, so this correction is known as the P2 integral, okay? So just correlator of two quadratic fields. Now, analogously, you can compute the correlator between the cubic field and the linear field. So let's see, if we're using the correlator without a prime, then there will be a delta function enforcing momentum conservation. But okay, it's something that's easy to keep track of. All right, now for the other integral, likewise, it's called P13. So now I'm going to strip off the delta function for simplicity. I'm going to find a different expression that involve now the cubic kernel. And I'm going to, again, streamline my notation and say that the integral over q vector is the integral over d3q over 2 pi cubed. Okay. All right. So now I can write down my final result. PSPT, nonlinear, is P11 plus P22 plus 2P13. And this is something that is called a P1 loop. So I'm going to explain why it's called like that in a second. Well, the idea basically is that if you have a perturbation theory of a random quantity, then your result of some perturbative calculation of any quantity can be represented in the form of Feynman diagrams. So this is true. I mean, we have experience with that in the context of quantum field theory, where we have quantum ensemble averaging and nonlinear interactions. Here we have a classical ensemble averaging and nonlinear interactions. But all the mathematical apparatus is completely the same. So even if we have a classical system, still we can represent our results in the form of loop diagrams. And you can see actually that the expression here looks very much similar to the usual loop diagrams in relativistic quantum field theory. Well, the obvious difference here is that, first of all, it's a three-dimensional case, right? And this is because we have an explicit breaking of the Lorentz symmetry here in our equations. And the second, because we're working in the non-relativistic limit. And the second important case here is that the coupling constants, these vertices, F3, F2, etc., they have a complicated momentum dependence. And this is something that normally doesn't happen in quantum field theory, where coupling constants are truly constants, like alpha strong or alpha electromagnetic, etc. Okay, so those are the only two conceptual differences that we need to keep in mind. But otherwise, we can totally come up with the diagrammatic technique that allows us to generate these loop corrections easily. So diagrammatic technique. Okay, so the idea is that we write down a graph that corresponds to the nth order correction to the total nonlinear matter over density. And we know by construction that this should involve n linear fields. So the way to represent this is to draw this vertex and a bunch of lines emanating from this vertex. And for the n vertex, we have n lines emanating. Then we have this vertex Fn, and that takes q input momenta and then outputs them to the final field by virtue of this delta function in the integral, q1, qn. Okay, so the sum of all these momenta should give us, should produce k, okay? So now if we associate, you know, if we say that this triangle with n lines emanating from it, if we associate this with the kernel times the delta function, then we can easily compute, you know, the nonlinear power spectrum. The only thing that we have to specify is the linear power spectrum. So this would correspond to the averaging over two, well, correlations over two initial fields. Whenever two initial fields meet each other and we correlate them, so we replace this diagram with a box, and the box corresponds to the linear matter power spectrum. And typically, since we have the momentum conservation in the form of k plus k prime, we can visualize this by the momentum k emanating from the power spectrum. Okay. Now, with these simple diagrammatic tools, it's easy to draw a diagram that represents P22. So this would correspond to this well, kind of sunset diagram. So you can see that both power spectra, they live inside the loop. So we have the momentum k, well, I guess we decided to draw them outgoing, momentum k outgoing here. Then we have momentum here q in the loop. The power spectrum will depend on p of k minus q and p of q. Now for the P13 diagram, the relevant graph will look like this. It will look like a typical, let's say, bubble diagram, right? So we have P11 of k picking out, right? Overall multiplication of this. So basically, the idea is for P13, we have three outgoing lines, and we contract two of them, and the other one is contracted with linear field, right? The linear field delta 1 just corresponds to this graph. Okay, so we have this P11 picking out outside of the loop, and okay, let me separate this. So this will be P11 of Q that sits inside the loop. And we have, you know, for the vertex, F3, we have an exact cancellation of the two loop momenta. All right. So now with this diagrammatic technique, we can compute higher order loops, and we can also compute more complicated correlators like the 3-point function. Okay, this is something that we're going to do later in the course. But at this point, okay, for the linear, for the nonlinear power spectrum at the first non-trivial order, so this is our result, P22 plus 2P13. All right, so let's see how this correction looks like. And before we look at the slides, I'm going to ask if you have any questions. Yes, please. Yeah. 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 That's right. Yeah, this is the way to think about this. Yeah, you have gravity, which is non-local, that sits in the fluid equations, and then you can write down like the action that generates this as well, but this action will look like a Euclidean action because time and space enter a different footing, and then this Euclidean theory will also be completely non-local because of the non-locality of gravity in the Newtonian limit. But yeah, the simplest way to think about this, like the closest analogy in other branches of physics, would be a condensed matter system, actually, with non-local interactions. That's right, yeah. So the propagator here basically is the linear power spectrum, which is provided by statistics, not by interactions. Yeah, sure. Any other questions? Yes, please. Yeah. Well, we've already accounted for it, right? It leads to an unobservable renormalization of the background, but we've already defined the kind of fully non-perturbative. We define the background at a fully non-perturbative level, right? So there is a scheme you can think about this as a scheme where you set to zero all these kind of bubble diagrams. Okay. All right. Well, in fact, what happens here additionally is that you don't even have to worry about this because the F2 kernel, when two momenta go to zero, also goes to zero, right? So you have an additional, like this diagram, in this particular case, will go to zero. Now, when we talk about the galaxies and bias tracer, that will not be the case, and this will lead to renormalization of the background density of the tracer, right? In this particular case, actually, the situation is simple because of the structure of these kernels. Yes, that is true also for Fn. Any Fn in the limit where one of them, when the sum of the method go to zero, the kernel goes to zero. So that's why this renormalization really doesn't change anything practically for dark matter specifically. Okay. Yes. Yeah. Good. Yeah. Thank you. So here, well, since the growth factor factorizes, I kind of absorbed it already here, right? So in practice, this means that you can just take P11 from your Boltzmann code from class, evaluate at the redshift that you want, and plug this in and compute the integral, and this will be the correction at the given redshift you're interested in. Okay. Yes. This is really an amazing question. At this point, yes, you should count the number of propagators, right? Like the linear result has one power spectrum. These things, they have two power spectra, but it's slightly more complicated because we ignored this TIJ at the moment. So TIJ will enter a power counting at some point. But historically, yeah, people just wanted to solve the fluid equations, as good as they can, and they would think that the effective expansion parameter would be the power spectrum itself, right? And we know the power spectrum, it's tiny at the CMB time is like 10 to minus 10, right? So it seems like a nice expansion parameter, but it's true that it has K dependence, which makes it slightly, different from the usual field series. Okay, any last question? Okay, if not, let's now study. Okay, let's first take a look at how these things look like. All right, so this is the one loop power spectrum, specifically these two corrections. Or here, I used a different notation where P13 here is 2P13 there, right? So there is no typo, but okay, it's a little inconsistency in the convention. Sorry about that. But the idea here is, well, you can see that this correction, indeed, for a very small case, when the power spectrum is kind of small, this correction is tiny. So it seems like, perturbation theory makes sense. So the first, well, here in this right-hand side plot, I'm plotting P1 loop and also some higher order corrections. Against the linear theory prediction, you see that indeed, the one loop prediction is small for most of the scales. Then at some point, it becomes as large as the linear theory prediction. This precisely happens at k.3, which I told you before corresponds to nonlinear scale. This is the scale where perturbation theory collapses. So this also makes sense. Now in this picture also, let me say that I'm plotting positive contributions with solid lines and negative contributions with dashed lines. So one funny thing that you can see is that on very large scales, the total correction, so the sum of P11, so P22 plus P13 is negative. So in fact, the first thing that nonlinearities do, they reduce power. And then later on, they enhance it. Okay, so this is an interesting feature. Now, I guess one interesting thing that you also see in this plot is that there seems to be a big cancellation between the P13 and the P22 integrals. And this cancellation has a lot of physical significance that I'm going to discuss now. So to understand better the behavior of the one loop power spectrum in a perfect fluid approximation, aka standard perturbation theory, let's consider the infrared and UV limits of the loop integrals. So paragraph 3.5, IR limits. And what I'm going to tell you now is that the IR behavior of this integral has a lot of consequences for the baryon acoustic oscillations. All right, so our limit, naively, for the integral such as P13, this corresponds to the case where the loop momentum is much smaller than the outgoing momentum, than the on-shell momentum. Okay. Now for P22, the situation is a little complicated because, as you can see from this expression, right, as you can see from this expression, is symmetric with respect to the exchange of Q and K minus Q, right? So because of that, in fact, it has two infrared domains. So one of them is the usual one, K much greater than Q, so Q much greater than K. And another one actually corresponds to the case where the outgoing momentum is much greater than the difference between K and Q. But because of the symmetry in practice, it just means that we need to consider one domain and multiply the result by a factor of 2, okay? Now, if I compute, if I take my integrals, and I take the kernels that were in my slide just before, and compute their infrared limit, right? So I'm going to Taylor expand in the ratio of Q over K. So I'm going to find that the P22 will look like this. So I'm going to introduce some sort of cutoff that defines my infrared domain. And then what I'm going to find here, the expression that we have seen before, is something that appears in the displacement variance. So in fact, this is exactly going to be given by the infrared part of the sigma v quantity that I introduced before. That measures, well, roughly how, the displacement along a single axis. Okay. Now, analogously, I can compute the leading order infrared result from the P13 integral, and I'm going to find the exact same contribution, but with the negative sign. So minus k squared sigma v IR squared. So you can see that 2P13 IR in order plus P22 IR at leading order, they cancel. And this is exactly what you see in the left diagram here. So you see that the net result of this cancellation is roughly an order of magnitude smaller than the individual loop contributions. And this cancellation, in fact, is, well, it has some profound physics. So this happens, as you can see from this expression, that so P22 and P13, they appear to be coupled to the IR modes. So in these integrals, the mode of interest K is coupled to the infrared modes via the displacement field, right? So in other words, it describes the situation when you have a mode with the wave number K, say K prime is the other mode, and then this mode is displaced by a long wavelength gravitational field. So you have a long wavelength perturbation that creates some gravitational field, and then our mode of interest, delta of k, accelerates in this field, right? But then, if you have another mode, I mean, we're computing two-point correlation function, right? We need a second mode. Now, the second mode also is here. It has a wave number which is much smaller. Sorry, which wave number is much higher. So the mode itself is much smaller than the long mode. So for both of them, this will look like a background fluctuation, right? That produces a uniform acceleration. So both of these overdensities are going to fall with the exact same acceleration, right? So which means that there is a frame where you can undo the acceleration in principle, right? So that means that in the two-point correlation, this whole, in the two-point correlation function, this whole acceleration story is just a coordinate artifact, right? That means that it should not have any physical consequences, and this explains the cancellation. So the key here is that the two overdensities, they fall with the same acceleration. And this follows from the equivalence principle, right? They should follow the same acceleration. Now, in terms of BSM, one interesting question might be is whether you consider two overdensities, let's say one overdensity of dark matter that respects the equivalence principle, and another version of dark matter, let's say a subcomponent of dark matter, that violates the equivalence principle and will feel a different acceleration. So in that case, these two contributions in a cross power spectrum will not cancel anymore. So this represents kind of a BSM case where we can look for some enhanced signatures, let's say enhanced P1 loop because of the violation of the equivalence principle. But for most of the normal theories for dark matter that respect the equivalence principle, this cancellation should always happen, okay? All right, any questions about this one? Yes. Yeah, they're coupled to a large mode, yeah. Good. Yeah, so these kernels, well, for instance, the F2 kernel will also generate the bispectrum. Yeah. So it's the exact same interaction that appears here, also will produce the bispectrum, and you can get the idea about this, Coulomb's principle by studying the soft limit of the bispectrum as well. That's right, yeah. Okay. Any other questions? Okay, so the leading effects cancel. Cool. Now, let's the subleading infrared effects. Subleading infrared effects. Okay, so SPT one loop of K in the infrared domain. So the contributions that does not cancel, this contribution will look like this. Okay, I'm going to write down all the coefficients just for fun. So you'll see that the finite infrared contribution, it will be proportional to the power spectrum itself, plus its logarithmic derivatives. And then the actual physical coupling constant, so that tells you how much the mode of the wave number k is coupled to the large scale fluctuations, it will be controlled by the mass variance of the infrared modes. So in fact, the relevant coupling parameter in the end is going to be just the mass variance of the infrared modes. That also makes sense. Once this thing is canceled, you can ask the question, what is going to be an actual physical nonlinear interaction effect on your mode delta k, on your mode k, with respect to some long wavelet mode? And the answer is that, if the mode has a very big wavelength, it will act like a local separate universe, and this local separate universe will have some mass fluctuation associated with this. So the tiny fluctuation that sees here will not be able to distinguish this separate universe from a global universe with some extra mass, right? That typically looks like like a closed universe with higher omega matter, right? So basically, the whole effect of the extra mode is to increase locally omega matter here, right? And omega matter is total mass. So the physical coupling then will be described by the total mass fluctuation carried by this long wavelength mode. And the mass fluctuation, so we know that it diverges in the UV, but in the infrared is actually very tiny. So the typical numbers we're talking about here is 10 to minus 2. So you can see that actual physical effect here is small, which explains the smallness of the finite correction. So in this regime, around the BO scales, your answer basically is dominated by the infrared modes, right? So K is large, Q is small. So this part of the power spectrum over here is described roughly by this formula. Okay. Now, all right, this seems fine, but remember we had this baryon acoustic oscillations, right? So at this point, looking at these logarithmic derivatives, you may start wondering, okay, we have this derivatives of the power spectrum. Now we have some oscillating function sitting in it. If we start hitting this oscillating function with derivatives, it's going to produce frequencies of the oscillation. And this frequency of the oscillation actually might be quite significant. So maybe this expansion actually could be problematic for this oscillating feature. And this is exactly what happens here. And to appreciate this, okay, to appreciate this, let's let's take a look at the matter power spectrum. So here I multiplied by K to enhance the wiggles. And you can see that more or less roughly you can represent the wiggly power, well, the total power spectrum as a sum of two components. The wiggly component, so P11 is roughly P wiggly plus P smooth, the broadband part. And then P wiggly roughly looks like some sort of envelope, smooth envelope, times the harmonic function. I'm going to call sine K over K oscillations. So now we try to estimate what different effects are doing. So if I compute the logarithmic derivative and logarithmic derivative of the smooth part of the power spectrum, so since it's smooth, it looks like a power law. This will scale roughly as coefficient, and then this is a tiny number, right? So it seems that for the smooth part, the infrared contribution is not problematic at all. You know, it's tiny, so perturbation theory makes sense. It's all good. Much smaller than P smooth. However, for the wiggly part, if we start acting on with logarithmic derivatives, okay, let's set the first derivative, we will see that it will produce a term that will look like K over K oscillations times, okay, F smooth times cosine. Now, the typical K's of interest for us are about 0.1 h over megaparsec, and K oscillations is roughly 1 over 110 megaparsec over h, right? So this is the scale of the BO feature and the correlation function. So which means that this factor K over K oscillations, in fact, is quite big, right? So this ratio will be roughly 100 times 0.1 is going to be 10, right? Okay, 10 times 10 to minus 2 is 0.1, so it seems to be fine at first order. But then you realize that we have this quadratic contribution as well. So for the quadratic contribution, quadratic NK, so we have K squared P double prime. So this will scale like K squared over k oscillation squared times sigma L squared. Now, this will be 10 to the minus 10 times 10 squared, so this is order 1. Okay, so it seems that we're in trouble. And in fact, now we can also estimate how the two-loop corrections are going to scale. And the two-loop corrections are going to scale as the leading order contribution, like k to the 4 times p to the 4, the fourth order logarithmic derivative, times sigma L to the 4, and this will be order 1 again. So you see that for the wiggly part of the power spectrum, the coupling to infrared modes becomes non-perturbative, right? So perturbation theory doesn't make any sense, and it seems that we're in trouble. And this will be true if we take a look at the two-point correlation function prediction in standard perturbation theory. So here in this plot, I'm showing you the two-point correlation function before. Now I multiply this also by r to the 4th power to enhance the BOP even more, just for visibility reasons, for illustration reasons. So the dots represent the n-body data. And you can see that linear theory, first of all, predicts a very sharp BO peak, but then the actual peak in the simulations is suppressed compared to that. So we're going to see shortly why the suppression should happen. But now if you try to just naively take this expression, well, in fact, not this, but the full expression, and compute the prediction for the nonlinear correlation function at the one loop order, you are going to find something that looks, well, kind of disastrous. I mean, it's true that the amplitude reduces, right, which is nice, but then you can see that the phase of the BO is completely distorted, right? So it seems that it's not doing a good job. And in fact, if you compute two loops, also it's going to, keep producing some strange wiggly oscillations. So clearly, this the expansion for the BEO, the perturbative expansion for the BEO in standard perturbation theory, at least we can say that it doesn't converge well, right? And this is the reason for that, because the effective coupling constant becomes order 1. Okay. Now, to see what the physical effect is associated with this nonlinear coupling, let me just evaluate. Let me take this expression and evaluate what this correction is going to look like for the wiggly part of the power spectrum. Let's just forget for the moment about this non-convergence. Let's just try to compute this naively, okay? So P wiggly at the one loop order will look like this: sigma L squared F smooth. So I'm not going to differentiate the smooth part because it's not interesting. The interesting results will be coming when the derivatives will start hitting the sign. So first of all, there will be a term that just is proportional to the wiggly power spectrum itself. So it doesn't do anything. So sine k over k oscillations. Then there will be a term that will look like this: 47 over 105 k over k oscillations. Now with the different phase, so cosine, because it has a single derivative, so it turns sine into a cosine. And finally, the last term will look like k squared over k oscillations squared times sine square, sine over k oscillations. Okay. Now, there are a couple of things here. So first of all, it's useful to recall some trigonometry formulas. So sine x minus epsilon cosine x. When epsilon is small, you can say that this is sine of epsilon. And 1 here is cosine of epsilon. So you can write this down as sine 1 minus epsilon. And second of all, we can take a look at these other expressions that appear in our P wiggly one loop. Well, we'll see that this expression, so this correction is tiny, right? It's just some number. times 10 to minus 2. So this is a very tiny result. Now this is potentially more significant and also distorts the phase. So we're going to absorb it into the sign with the shifted argument. So you should remember that we also, okay. So we also have the usual part from the linear theory that has sine k over k oscillations. Plus we have p wiggly, one loop. So let's ignore this term, it's tiny. This term distorts the phase. This term doesn't distort the phase, but it suppresses the amplitude, right? So we can write this down, again, assuming that sigma L is tiny, which is true. We can write this down as p wiggly of a different argument, k over k oscillations, 1 minus 47 over 105, sigma L squared, times 1 minus 1 over 10, k squared over k squared oscillations, sigma L squared. All right. So we see two effects here. First of all, we see the shift of the BO scale. And this shift is controlled again by the large scale variance. So the physical reason for that is that the mode with the wave number k, when it's coupled to a large wavelength fluctuation with the variance, mass variance sigma L, it will effectively live in a closed universe with larger omega matter. And in that case, well, in a different universe, with different cosmology, well, the universe will be closed. And then in this case, effectively, the rulers are going to shrink. So in an open universe, a fixed ruler will have a smaller, because of non-Euclidean effects, it will have smaller length. So this is why the BEO scale effectively shrinks. And this effect already pops up in this IR approximation. And in fact, even though we expand this effect in the infrared modes, etc., but this result is exact, right? There are no corrections to this result. Now, a second important fact is the suppression of the total amplitude of the wiggly parts, right? So this you can see as a suppression of the, ultimate suppression of the BU feature at the nonlinear level. You can see it's smaller than the linear theory prediction. So here you see the first kind of toy version of the suppression. And in fact, this result is not exact at the moment because this expansion that we had before in terms of the derivatives, if you have an oscillating function, it makes sense only for modes that are smaller, so only for the Q modes that are smaller than K oscillations. But in principle, this effect also receives correction from modes greater than K oscillations. And then the full result will look like this. So it will be proportional to the difference between these two loop power spectra weighted with 1 over q squared. So this 1 over q squared is responsible for the extra enhancement due to, in the infrared domain. And in principle, you can see that for modes, so for q, which is, so in principle, this effect receives contributions all the way, from q's as great as k. So you receive corrections to the damping of the BEO feature all the way to k's. And in this case, you can say that this is roughly, this whole thing is roughly of the order of P of Q. So the total effect is going to be proportional to K squared times sigma V squared. Again, the sigma V is related to the variance of the displacement field. And this is big, so this is an order 1 number. So we discussed before that the typical nonlinear scale that we're talking about corresponds to 0.3 h over megaparsec, right? So this is like, we're talking about megaparsec type scales. Now this scale is 6 megaparsec, right? It's much greater than that. So this effect again becomes non-perturbative. So this is very bad. Within the standard perturbation theory, it's very hard to fix it. Well, basically there are two ways to do it. The first way to do it is to generate all possible diagrams and then look at them long enough time and see which diagrams produce this kind of enhancements. And then resum those diagrams at every order. So that's why this procedure in general of resumming the large infrared effects is called infrared resummation. And the first way to do it is to resum on a diagram by diagram basis. And this is realized in a framework called time slice perturbation theory, which is basically a new way to formulate perturbation theory that has nicer diagrams that make the infrared properties manifest. Now, another way to deal with this problem is to use Lagrangian perturbation theory that I talked about last time, where the relevant quantity is not the density and velocity field, but the displacement field defined by relating the, well, looking at some fluid element at the initial time, or let's say fluid particle, and writing down the field that tracks this particle later on during the evolution. So in this picture, this effect appears to be because of the nonlinear relationship between the density field and the displacement field. Turns out that this effect of IR resummation and suppression of the BO already shows up at the linear order, at the first non-trivial order, which corresponds to the Zeldovich approximation, right? So this Lagrangian perturbation theory is nice because if you compute the linear order result, you're going to resum all these IR effects automatically. So that's why this is one of the reasons why Lagrangian perturbation theory in some sense superior compared to Eulerian. But again, you can look at things diagram by diagram and you can basically achieve the same answer, and then you can prove that for this particular observable, the two approaches give you the same answer. So I don't have much time to go into Lagrangian perturbation theory now. I will hopefully have time later on, maybe in my last lecture, where I discuss how this is going to work. At this point, let me just say that, so these things have been worked out, and the result, the final result of IR resummation will look like this. Pw of k minus sigma squared k squared, where, so you see that the suppression exponentiates, and the relevant scale that appears as a result of this IR resummation will be determined by the following expression. So this expression features spherical Bessel functions that depend on the ratio of the loop momenta in the IR domain over k oscillations. And you can see that, so if we ignore these brackets, this is just the usual infrared displacement, right, that we discussed before, the variance of the infrared displacement. So the coupling to this displacement is forbidden by the equivalence principle. And these things, these Bessel functions, they precisely enforce this. So we can calculate sigma squared in the limit where q is much smaller than k oscillations, and it will be given exactly by 1 over 10 k squared over k oscillation squared times sigma L squared. So this is a very important part of the full kind of accurate infrared resummation, but it respects the equivalence principle, and in the limit of very, very large modes, the coupling again is given by the mass variance, right? So historically, people just realized, they looked at the simulations, they looked at this result, and they thought that, oh, if we just take this IR displacement without this part, and apply this formula, we're going to nicely describe the suppression of the BEO. And at practice, it worked. And it worked only by accident, because the IR part of this integral that gets weighted with these guys it's very small, right? So it gives a tiny contribution to the actual displacement. So a lot of the signal here, like this integral, the integrand of this integral is peaked around the peak of the linear matter power spectrum. So it's peaked around here. So that means that everything that happens before that or after that kind of doesn't matter, and the integral of the IR displacement variance also peaks at k quality, right? So the two integrals, the one with the proper weight and the one without the proper weight, they just happen to coincide numerically. If our universe had been different, if we had more power on very large scales, the two would be different. And obviously it would make sense to use the correct expression, but just historically people realized that, oh, this gives a good fit to the data, and they kept using this expression. And even now I think that in some of the survey papers they use the expression computed without these things, which again provides a good numerical answer, but ultimately conceptually is wrong because it violates the equivalence principle. Okay, so this is something to keep in mind in general large-scale structure theory, that a lot of things happen to work only by accident. Okay. All right, very good. So that is the end of the infrared story. Let's talk about now the opposite limit, is the UV limit of loop integrals. Yeah, and once you have some slide. All right. Yeah, once you implement this and you propagate this IR summation to higher orders, then you can nicely describe the suppression of the BEO. So this is one of the big achievements of effective field theory, that basically you can describe the suppression of the BEO peak and also the shift very, very accurately to level of per miles. And this is something that you cannot achieve by just doing this simple kind of hand-wavy arguments. Okay. Are there any questions? Okay, if not, let's take a look at the UV limit of loop integrals. All right, so this will be paragraph 3.6. Okay, UV limit is pretty straightforward. So this is the limit where the loop momenta is much greater than the external momenta. Again, we can now tailor expand the integrands of our integrals P22 and P13, and we're going to find the following expression. So we're going to find for P22 that will be some numerical coefficient, then k to the 4, and then the integral in the UV domain now. So for the very hard modes. Now the one interesting thing that will happen for P22 is that since it's a convolution integral for large Q, you will have two P of Q's, right? So the power spectrum will sit entirely inside the integral in this limit. And physically, way to understand this, so it doesn't have any dependence on P11 of K, right? It's not proportional to P11 of K, which is an interesting result. So physically, this tells you that on very small scales, the UV modes decouple, and then they produce some contribution to the power spectrum on large scales proportional to the k to the 4, but this contribution is not correlated anymore with the initial conditions, right? So you have this decoupling situation. Now, the other integral, P13, well, we know that for the P13, we have the linear matter power spectrum sitting outside of the integral, right? So we're going to get something that is proportional to P11 of K. And indeed, what we're going to find is that P13 of K will behave like minus 61 over 630 pi squared, some constant. Then there will be dependence proportional to k squared. Simple integration in the UV domain. And now this integration will involve the displacements of the UV modes, right? So this is again the displacement variance, the integral over P of Q time with the measured one, right? Without d3q, right? So this is the typical displacement situation. Okay, so physically what happens is that you have a mode K. Now K is a big mode, right, with respect to Q. And you have all these small scale modes that have some complicated dynamics. And they kind of modulate, they pull the modes, the large scale mode in different direction. And in fact, you can see that when you average these different displacements that try to pull the mode in different directions, you're going to get a suppression, right? So you're kind of stretching the mode, right? You're suppressing the power. So you're going to stretch it as a result of the small scale displacement. So this explains why in this calculation that we found here, that we looked before, so this explains why the large scale limit is negative. So the very first thing that the nonlinear clustering does, it actually suppresses the power. Okay. Okay. Now we can ask the following question. Okay, we have some expressions in the UV, right? Do we know if these expressions converge? So is that the P, so if we, let's say the following, if we assume that P of Q is a power law that behaves as Q to nu, Q to the nu, okay, let's, it diverges if nu is greater than 1/2 and the P13 diverges if nu is greater than minus 1. Okay. So first of all, the question is, okay, we have these divergences. So what happened if the power spectrum in our universe would satisfy this or that? What we would see? I mean, we would see that these integrals just will not converge. The result will not make any sense. And for a very long time, again, people were confused about this. They were saying that, oh, this somehow these power law indices, they're inconsistent with like a bigger cosmological picture. There is some mathematical consistency with them. But now with the quantum field theory background, we know that when something like this happens, it doesn't mean much, right? It only means that you're trying to extrapolate the result of your perturbation theory to a regime where it doesn't apply, right? So the right thing to do is to cut off this integral, but then you have to remove the sensitivity to the exact cutoff that you're placing, right? You need to introduce some sort of counter terms. And in this particular picture for the standard perturbation theory, well, as you notice that we didn't introduce any free parameter whatsoever. So we don't have any means of renormalization. We don't have any means to absorb these divergences. So what happened is that in the actual universe, both these integrals, they converge, right? But again, they converge to a wrong answer. But for a very long time, people didn't realize that just because they converged. And the worst part of it is that the UV dependence at this order is not very strong. So when people, computed this one loop SPT correction and they tried to compare it against the data, they saw that at the very beginning they capture correctly the suppression, like the onset of nonlinear structure formation that produces the suppression due to small scale displacements. So the usual one loop SPT calculation kind of captures this. Then eventually it blows up. You see it overshoots. But somehow people kept thinking, okay, this is probably because we only did one loop. Let's do two loops. They did two loops. Two loops, describe the data a little bit better. So because of that, for a long time, people were thinking, oh, maybe we're on the right track. Let's try to compute more terms, resum, resum, do something. And you can find a lot of papers on resummation and things like that on arXiv. But with the EFT background, we know that they all diverge these perturbation theory predictions don't make any sense because of two things. First of all, because these loop integrals, they converge to the wrong answer, so they're never going to give you the right things. And second of all, because we ignore the stress tensor, right? So the perfect fluid description itself is an approximate thing, right? It doesn't matter how well do you solve an approximate theory because it's still going to be approximate. So all these problems are fixed only if you move on to the full EFT picture and include the contributions from the stress energy tensor, which we'll have 5 minutes. So probably this is something that I'm going to leave to the next lecture. And I'm going to take your questions right now. Yeah. 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 That's right. Okay, so the statement is that you have these leading IR effects that are big, right? And that they cancel because of the equivalence principle. And then there are subleading effects that are totally cool with the equivalence principle, right? That are totally fine with the equivalence principle, right? So when you violate EP in dark matter, okay, first of all, you need to calculate the cross spectrum. Okay, this is fine, we can do that. But yeah, in that case, the P1 loop will be enhanced. But if you go, so it's a very nice effect for dark matter. Now for tracers, the problem is that this enhancement is very hard to detect because it's proportional, the residual of this cancellation will be proportional to k squared, right? And for k squared, well, as you see kind of from the discussion, you also have some k squared contributions from the UV modes, right? So there will be some degeneracy. A better way to look for this effect, so it's true that there will be an effect at the level of the one loop power spectrum, but this effect will be hard to extract because of degeneracy with other things. So better observable would be a bispectrum of different tracers, because all these kernels that I introduced today, they also generate higher order endpoint functions. Like the F2 kernel generates the bispectrum. So this cancellation of the equivalence principle, cancellation of things is encoded in the structure of the F2 kernel that will have a different expression in the EP violating models. And then the F2 kernel will appear in the bispectrum, and even on large scales, we can test its structure so we can extract the EP violation principle. So better channel would be. That's right. Yeah, the bispectrum is exactly that. Yeah, yeah, right. Cooper. Yeah. Yeah. Oh, it's going to be okay. So the statement is that, yeah, in principle, KUV would be KNL. So you would do your integral up to KNL. So you can trust your theory up to KNL. And then the rest of it you cannot trust. So if you're using the KNL truncation, like a finite cutoff truncation, then the question will be that your predictions now will depend on the exact choice of KNL you're using, right? And that's why you have to introduce counter terms to kind of to account for it, to remove this ambiguity. In a more kind of traditional way, what you would do, we would compute like KUV. You would say that this is some UV cutoff lambda, right? And then your prediction will start to depend on lambda. You would want to introduce counter terms to remove this lambda dependence. right? So this really depends on the type of regulation that you're using, or the scheme dependence, right? You can have a scheme with lambda, you can have a scheme with like k-nonlinear and everything else, but altogether, like it's the same thing, just using different words. That's right, yeah. That's right, yeah. So in practice, actually, what we do, since these integrals converge, we evaluate them all the way to infinity and then compensate for the error introduced by that. So this turns out to be more convenient than putting a cutoff. But if you want to estimate, let's say the actual physical size of one loop, um, you can do that by cutting it off at k-nonlinear. And this is something in particle physics that is called naturalness, right? And like seq work was discovered like that. Okay. Yes. Right. Yeah, now, yeah, it will be still there, but now it will apply to modes around k-nonlinear. The same logic will be there. Okay, so the story is that you have some integrals. So for any k less, so this is what defines your UV domain, right? But then now you can say you can introduce k nonlinear, right? And k nonlinear, well, for instance, k nonlinear can be, so the UV domain introduced like this is quite broad. So for instance, it also involves this situation where you have modes Q that are still within kind of quasi-perturbative scales, right? And in that case, yeah, you have small modes whose wavelength is much smaller than a large mode, and then they will be coupled to a large mode via the displacement, and they'll be producing like a physical effect of this stretching. And this is what you see, even if you account for, renormalization and things like that, like you can see that this is a physical effect associated with this, right? This is the suppression, right? So this is the exact like physical intuition behind the suppression that will still be there for these modes. Okay. Yes. What it means here is basically the fact that when you compute these things, you have big corrections for the wiggly part, and then IR resummation means that you just take a look at your diagrammatic expansion or perturbative expansion, and you identify terms in this expansion that are big, and then you resum them, which means that you just keep all these terms, and you will see that this expansion, Taylor expansion over these terms, can be nicely resummed into an exponent. And in particle physics, similar things happen when you want to account for infrared effects associated with soft modes, and that's why we use the same word for it. But really, it's nothing fancy. It's like really you did some mistake setting up perturbation theory by expanding over the density field. Now, this density field itself also is contained in the IR displacement, which is big. So you did a mistake. Now you need to sum it back. Okay, and in Lagrangian perturbation theory, you never make this mistake. So that's why it's very nice, and it kind of IR sums everything automatically. Yes. Yeah. That's right. Yeah. Oh yeah, absolutely. So well, I erased this, but you remember there was this equation with terms like this, right? So basically, this is something that looks like this, from which you can recognize a dilation operator, right? So basically, if you look at the total power spectrum, let's forget about this p wiggly. Okay, so the IR modes, they produce these dilations, and this is what people call beat coupling or things like that. And this is in fact important also in supersample covariance. Yeah, it's just a coupling. Again, from this perspective, just a coupling between mode of k and a large mode that is contained in perturbation theory. Okay. Yes. Oh, all normalizations here, yeah, very similar. You see, the thing here is that you don't have anything like gauge symmetry, so that's why we can do whatever we can use whatever in normalization scheme and it will be fine. But in practice, it's actually true that we're using dimensional regularization, which is nice because all convergent integrals then are computed, and then divergent integrals are set to 0. And it's true that you will have some error by extrapolating integrals to infinity, but then you subtract this error by the counter terms. So this is what we actually do in practice. It's very similar to what people normally do in renormalization of gauge theories. Yeah. Okay. Thank you.